Welcome back to G Fun Facts Online. Today we are diving deep into a technological frontier that has frustrated engineers for nearly a century, a gap in our reality that we are finally closing. We are talking about the silent spectrum, the Terahertz Gap, and the quantum revolution that is about to change how we communicate, how we see inside the human body, and even how we look at the stars. We are talking about the atomic antenna. To understand the magnitude of this shift, we have to look at the electromagnetic spectrum. It governs everything in modern life. We have radio waves carrying our music, microwaves heating our food and powering our radar, and infrared light that we feel as heat. On the other end, we have X-rays scanning our bones. But right in the middle of all this, sitting comfortably between the microwaves used in 5G and the infrared light, lies a notorious no-man's land known as the Terahertz Gap. This band, approximately 0.1 to 10 terahertz, has been a technological dead zone. Physics just didn't want to cooperate there. For decades, engineers have looked at this gap with longing because terahertz waves have superpowers. They can penetrate materials like clothing, cardboard, and wood, just like radio waves. But unlike X-rays, they are non-ionizing. They are harmless to biological tissue. They hold the potential to carry vast amounts of data, promising wireless speeds up to 100 times faster than current 5G networks. But harnessing them has been a struggle. They are too fast for traditional electronics to process effectively, and too slow for standard optical photon detectors to see without extreme cooling. This is where the story changes. We are currently witnessing a paradigm shift in how we detect and measure electromagnetic fields. We are abandoning the metal rods, loops, and dipoles that have defined radio for a century. Instead, we are turning to nature's own perfectly identical sensors, atoms, specifically Rydberg atoms. These are the giants of the microscopic world. To understand the atomic antenna, you have to understand the peculiar physics of the Rydberg atom. Named after the Swedish physicist Johannes Rydberg, these are not your ordinary atoms. In a typical atom, like the rubidium atoms used in these sensors, the outer electron orbits relatively close to the nucleus. But if you bombard this atom with a very specific frequency of laser light, you can kick that outer electron into a highly excited state. In quantum mechanics, we describe this with a principal quantum number, n. A normal atom might have an n of 5. A Rydberg atom can have an n of 50, 80, or even 100. The physics here gets incredible. The radius of an atom scales as n squared. So a Rydberg atom with an n of 100 is 10,000 times larger than its ground state. If a normal atom were the size of a marble, a Rydberg atom would be the size of a hot air balloon. This massive size makes them exquisitely sensitive. The sensitivity of an atom to an electric field depends on its electric dipole moment, essentially how stretchable the electron cloud is. A Rydberg atom is millions of times more stretchable than a normal atom. Even more dramatic is its polarizability, which scales as n to the power of 7. This means the atom's reaction to an external field is amplified by a factor of trillions. When a faint terahertz wave passes by, it grabs onto this loosely held electron and shakes it with ease. This makes Rydberg atoms the ultimate antenna. In a classical antenna, a radio wave pushes electrons back and forth along a metal rod. But for terahertz waves, which have wavelengths of fractions of a millimeter, making perfect metal antennas is a nightmare. The metal becomes resistive, turning the signal into heat. A Rydberg atom bypasses this entirely. It doesn't conduct electricity in the traditional sense. It's a quantum sensor. And because every atom of a specific element is identical by the laws of physics, this antenna never needs physical calibration. It is defined by universal constants. So how do we actually read the signal caught by a single atom? We can't attach a wire to it. Instead, we use light. The core of an atomic antenna is a small glass cell, a vapor cell, filled with a gas of alkali atoms like rubidium. We shine two lasers through this cell. The first is a probe laser, which the atoms would normally absorb, making the cell look opaque. The second is a coupling laser, tuned to excite the atoms into that giant Rydberg state. When you tune these lasers just right, a quantum phenomenon called electromagnetically induced transparency, or EIT, occurs. The atoms, which were blocking the light, suddenly stop absorbing it. The glass cell becomes transparent. If you put a detector behind it, you see a bright beam of light passing through. This is our baseline. Now imagine a terahertz wave. The signal we want to detect passes through that glass cell. The frequency of this wave is chosen to match the energy gap between two adjacent Rydberg states. When the wave hits the atoms, it disturbs that delicate quantum interference that created the transparency. For strong signals, this causes the light peak to split into two, a phenomenon known as Otler-Town splitting. The distance between the split peaks tells us exactly how strong the signal is. For weaker signals, the terahertz wave causes a shift in the intensity or phase of the light. By monitoring the light coming out of the cell, we can instantly hear the radio waves. If the terahertz signal carries data, like a 6G internet connection, The light intensity fluctuates in perfect sync with that data. We just convert the light into an electrical signal using a fast photodiode, and we have recovered the information. This entire process happens at room temperature, which is a massive advantage over older technologies like bolometers that required liquid helium cooling to work. But the story doesn't stop at basic detection. Recent research in 2024 and 2025 has pushed this technology into the realm of the magical, with a technique called six-wave mixing. While standard EIT is great for measuring field strength, it struggles with very weak signals, like a whisper from a distant galaxy. Six-wave mixing changes the game. In this advanced setup, the lasers force the atom to absorb a terahertz photon and immediately emit a visible photon, say a green or blue one. This is crucial because we have amazing detectors for visible light. We can detect single photons of visible light with over 90% efficiency. By converting the hard-to-see terahertz photon into an easy-to-see visible photon, the Rydberg sensor inherits that extreme sensitivity. This allows for a noise-equivalent power that is orders of magnitude better than the best room temperature thermal sensors. We are talking about detecting signals billions of times fainter than what was previously possible without cryogenics. This leads us directly to the applications, starting with the revolution in telecommunications. 6G. The world is hungry for data. 6G envisions data rates of 1 terabit per second. That is fast enough to download 100 movies in a second, or stream holographic video in real time. To get that speed, we have to move up to the terahertz frequencies. Current experimental 6G receivers are complex, expensive, and power-hungry. They use electronic mixers that are pushed to their breaking point. Researchers are now developing Rydberg atomic receivers for 6G. These sensors have massive bandwidth. In fact, researchers have already demonstrated streaming high-definition video over a terahertz carrier using a simple vapor cell. What's even more fascinating is that the atoms act as the mixer themselves. You don't need complex demodulation circuitry. The down conversion happens quantum mechanically, simplifying the entire receiver architecture. Plus, because the antenna is just glass and gas, it has a very low radar cross-section. It's transparent to other radio waves, which is a huge stealth benefit for secure communications. Beyond speed, these sensors offer a leap forward in medical imaging. Terahertz waves are non-ionizing, meaning they are safe, but they are very good at differentiating between tissue types, especially based on water content. Tumors often have higher water content and different blood flow than healthy tissue. A handheld Rydberg scanner could detect skin cancers or breast tumors without any radiation risk, potentially spotting anomalies much earlier than current methods. They can also precisely determine the depth of burn wounds, helping surgeons decide if skin grafts are needed without invasive probing. In the world of security, this tech could replace those bulky spinning scanners at airports. Because of the high sensitivity of Rydberg atoms, we could have passive walk-through corridors that sniff out the spectral signature of explosives or weapons hidden under clothes from a distance, without slowing down the flow of people. The engineering race is now on to miniaturize this technology. We can't put a laser table inside a smartphone. Engineers are developing chip-scale atomic devices. They are using microfabrication to make vapor cells the size of a grain of rice and etching waveguides directly onto silicon chips to deliver the laser light. The goal is to create a sensor module no larger than a matchbox. Companies like Rydberg Technologies and Inflection are already commercializing this, and major defense contractors are integrating these sensors for their wideband capabilities. Finally, the sensitivity of the atomic antenna opens doors to fundamental physics. One theoretical candidate for dark matter is the axion, a particle that would interact very weakly with electromagnetic fields. Some experiments are now proposing to use Rydberg atoms to listen for the faint radio hum that axions might generate. In astronomy, looking at the universe in terahertz frequencies allows us to see the cold universe, the dust clouds where stars are born. Current telescopes need heavy cryocoolers. A room temperature Rydberg sensor could allow for lighter, cheaper satellites that can still peer into the stellar nurseries of our galaxy. We are standing at the threshold of a new era. For over 100 years, we have relied on the motion of electrons in metal, a classical phenomenon. Now, we are moving to the quantum motion of electrons within a single atom. The atomic antenna is not just a better antenna, it is a different kind of antenna. It breaks the rules of bandwidth, sensitivity, and size that have constrained engineers for decades. From 6G networks that beam holographic data to our pockets, to medical wands that see healable wounds, to telescopes that scan the dark edges of the universe, the Rydberg atom is the key. The future of wireless is not just faster, it is quantum, and it is being built, atom by giant atom, right now. Thanks for listening to G Fun Facts Online.